Okay, YouTube, in our last video we kind of mentioned this idea of inverse functions. And this idea of inverse functions basically says that for some input, we would say that usually this is some x value. If we put that into a function f, then it'll map over to some f of x value. What we want to do is come up with some other function, and we usually refer to this as f inverse or some other g of x that is the inverse of f there. But basically what would happen is if you were to take f inverse of x and plug our f of x values into it, then it goes back to the original x value. So the neat thing about inverse functions is that inverse functions undo one another. And so what we want to be able to do is, given a function, can we go find its inverse? And so this is always the case that we can find its inverse. The key lies in the fact that two functions are inverses if and only if their domains and ranges, that would be their inputs and outputs, these things over here, or their x's and y's switch around. So since that's the case, then we could just use this set of steps that I've outlined here to find inverses. So step number one, sorry, before I even get to step number one thing that I want to mention here is this. Domain and range switching, you can notice that what we plug in to our original f value are all these x values here. And so this is the domain, what we'd say, of f. And so this would be the range of f, because these are the values that we get once we plug the x values in. Now when we look at f inverse, the interesting thing is, what are we plugging into f inverse? You'll notice that the initial part of this arrow is over here in the range of the original function. So this becomes the domain of f inverse. So the domain of f inverse is really all the range values of f. But what we map these f values back to are these original domain values, which now become the outputs for our inverse function. So we say this is the range of f inverse. And so that being said, essentially what this means is for every point on one graph, all of the points here y on the other graph are going to go right back to x. And so we could see that these domain and range values switch. So with respect to finding inverse functions, just remember that the steps are pretty easy. Step number one is just this. We're going to take all the x values and switch them with the y values in the equation. So this should look the same as the original function, but basically we should have all the variables switched. And then what we're going to do there from there on is basically solve for the value of y. And so I've got a couple of clauses underneath here that we'll take a look at here in just a moment, but let's go ahead and start with what we've seen so far. Step number one, we have this inverse function here. It says find the inverse of each function. F of x is this function we've gotten is 6 to the power of x. What I'm going to do is, first things first, I'm going to rewrite this in terms of y's and x's. Because the very first thing we need to do is to find the inverse here. And I'm going to change colors. Let's put this in red, because once I put this in red, it is the inverse. We would say that the inverse function that has a switched domain and range really is the function x equals 6 to the power of y. So by taking all of our x's and y's and switching them around, what we've done here is we've given a new function that basically we have switched the domain and range. Now, when it says on number 2 here, solve for the value of y, the interesting thing is we don't really have a way of solving for y, or do we? And that way is just basically going to be this. We would say that if we were to rewrite logarithmically, logarithmically. How do I know it's supposed to be logarithmically and not exponentially? Well, what form is it in right now? It's exponential form. So if we go rewrite this logarithmically, what we end up getting is this. We would say log base something of something turned into something, not turned into something, but is something. We'd say, well, what's our base here? And on our expression here, I have a base of 6, so we have log base 6, and we would say that 6 to the power of something turned into this thing. Well, really, we say 6 to the power of y turned into x. So we would say that this thing right here is our inverse function, but the reason why is because we have isolated y in the function. We got y by itself. So the last thing we're going to do, and this is just a step that I didn't put up here, number 3, but from time to time people ask you to write this as the inverse function. So instead of y equals, what we're going to do is we're going to say that this is some inverse function, and the inverse function is log base 6 of x. So you can see that 6 to the power of x is the inverse of log base 6 of x here. So now looking at a situation where we start with something logarithmic, something like this. I'm going to say y equals the natural log of x plus 3 here. One thing that I want to say about this is that the natural log of x plus 3 is never going to be, at least in your lifetime, equal to the natural log of x plus the natural log of 3. Okay? Or at least, I suppose that I can't think of any values that would cause that to happen. So Since that's the case, what I want to do is go ahead and rewrite this as what it actually is. And so this is not often something that people do, but I'm going to rewrite it this way. We say log base e of x plus 3. So in terms of what I would do here, I would rewrite this. Sorry, not rewrite yet. This expression here, we're going to rewrite this. Yeah, rewrite this where our x's and y's switch around. So we're going to say x equals log base e of y plus 3. Now the hard part about this, or at least it seems hard at first, is that we need to get y by itself here. And so what you're always going to do is this. We're going to rewrite. And this is where I had intended to write the word rewrite, but we'd say rewrite exponentially. Okay. That is to say that if it's in logarithmic form, that's what I write up here. If a logarithmic function, then you'll need to rewrite it exponentially to isolate y. When we look at this here, if we were to rewrite this exponentially, we say e to the power of x turned into y plus 3. Let's go ahead and rewrite that here. We say e to the power of x is y plus 3. You could see that it's a lot easier to get y by itself here because all we have to do is subtract the 3 from both sides. So what we end up with is really y is e to the x minus 3. But if y is e to the x minus 3, then we'd say its inverse is y equals ln of x plus 3. So these two functions would be inverses of one another. Now one thing that I want to make sure that we do here before we piece out of this video totally is this. We said that this function down here was our inverse function of x. And the original function f of x was this function right here. We're going to call this f of x equals the ln of x plus 3. So what I'd like to do is show you that these functions do indeed cancel each other out when we compose them, when I plug one into the other one. So let's do this. Let's take f inverse of x, and we're going to plug it into f of x. So we say f of x is given by ln x plus 3. So we're going to see that this ln x plus 3 really becomes this right here, where instead of x, okay, what we're putting in is f inverse of x. So by substitution here, we'd say, well, that f inverse of x really is the same thing as e to the x minus 3. We get e to the x minus 3. Combining like terms in here, the first thing I notice is that those 3's cancel out and we get left with ln of e to the x. But if we know our inverse properties of logarithms and exponential things, we are taking a logarithm of an exponential expression. And just to point this out here, we would say that, check it out, both of these have the same bases. And so in this case, those two things would cancel each other out, and what we get left with is just this x. So it really did happen that when we composed these, we were able to send the outputs of f inverse back to the original inputs, x, and so that these must be inverses of one another. Cheers.